Hello, welcome to this video. In this video, let us take a problem on Otto cycle. Now, in a constant volume Otto cycle, the moment I see the constant volume Otto cycle, I will draw PV as well as TS diagram for an Otto cycle. So, let us draw PV and a TS diagram for an Otto cycle. So, pressure versus volume, temperature versus entropy. We know that in a PV diagram, we are going to compress it by reversible adiabatic compression. Then we have constant volume heat addition or heat supplied 2 to 3. Then 3 to 4 is again reversible adiabatic expansion. Then 4 to 1 is constant volume heat rejection. So, heat rejection. So, in TS diagram, okay, let us write this PV power gamma is equal to constant, PV power gamma is equal to constant. In TS diagram, we know that 1 to 2 would look like an isentropic process because that is PV power gamma or reversible adiabatic or isentropic compression. Then constant volume heat addition, this is where our heat is added. And then 3 to 4 is constant volume, reversible adiabatic expansion. And again 4 to 1 is constant volume heat rejection. So, this is our entropy constant or PV power gamma constant. Now, the pressure at the end of compression is 15 times that of the start. That means, pressure at the end of compression is denoted by P2. Pressure at the end of compression is P2, right? Because we are compressing from 1 to 2. So, P2 is 15 times of P1. So, pressure at the end of compression is 15 times of that of the start. So, start is P1, so 15 times of P1. So, and the temperature at the beginning, temperature of the air at the beginning is 38 degrees Celsius. So, 38, let us convert that into Kelvin, 38 plus 273, 311 Kelvin. And a maximum temperature attained in the cycle. So, maximum temperature comes at 3. So, you can see that in TS diagram as well. So, T3 is given 1950 plus, let us convert this into Kelvin, 1950 plus 273. So, 222 3 Kelvin. All right. Determine first one, compression ratio. So, we have been asked to calculate compression ratio. Second one, thermal efficiency. And we have third question, that is work. And we have been given that the value of specific heat ratio or gamma is 1.4. Now, let us go for compression ratio. Now, how do we calculate compression ratio? I think we can consider process 1 to 2. We can consider process 1 to 2 and we can write P1 V1 power gamma is equal to P2 V2 power gamma, because that is PV power gamma is equal to constant process. And we have this ratio actually P2 by P1 we have, because this is nothing but P2 by P1 is equal to 15, correct. So, P2 by P1 is equal to 15. So, I will write P2 here, P2 by P1 is equal to V1 by V2 whole power gamma, which means V1 by V2 is nothing but compression ratio. So, R power gamma is equal to P2 by P1, or you can write that R is equal to, if this gamma comes here, it will be 1 by gamma here. So, that means P2 by P1 is 15. So, 15 power 1 by 1.4. So, that way we can find out the value of R, and we also know the range. R value for any engine will vary from 8 to 15 or something like that. So, for a petrol engine it will be 6 to 8 or somewhere in that range, whereas if you are talking about compression ignition engine, it will be little higher. For Otto cycle it will be 6 to 8, that will be the range, little here and there is okay. Now, 15 power 1 by 1.4. Yeah, 6.91 is good. So compression ratio for this particular engine is 6.91. Now the moment I have compression ratio, it is easy to find out the value of thermal efficiency, correct? So because this is our sub question 1 or sub question A. Now sub question 2 is efficiency is equal to, we have this 1 minus 1 by R power gamma minus 1 for Otto cycle. So 1 minus 1 by 6.91 power 1.4 minus 1. So that is nothing but 1 minus 1 by 6.9491 power 0.4. So let us solve that. 1 minus 1 by 6.91 power 0.4. So 0.5384, which will have to multiply by 100, which is nothing but 53.84 percentage. So 53.84 percentage. Now let us go to calculate the work. Now how can we calculate work? So calculate work transfer. Now work transfer can be calculated by, if we can calculate heat supplied and heat rejected, that is one way of doing it. Because we have efficiency, efficiency can be used in other way also, that is desired output, that is work transfer divided by heat supplied. If we this way value we already have, if we can supply QS, then I think we can calculate W. So let us calculate QS. Now how can we calculate QS? Now QS is equal to, heat supplied is happening at constant volume, right? So MCV dt for constant volume. So for constant volume, the heat supplied is MCV T3 minus T2. MCV T3 minus T2. We have not been given the value of M, so we will assume that we are doing it for 1 kg. So unit will be per kg, all right. So let us assume that it is simply CVDT, because we cannot calculate M with the given data. Now CV for air is known to us. CV for air is 0.718 kilojoule per kg Kelvin. Now T3 is already known to us. If we calculate T2, I think we can calculate QS. Now how do we calculate T2? So that is very well known to us. T2 by T1, we know that either you can derive it from the start. So T2 by T1 is equal to R power gamma minus 1. So how did we arrive at this equation? So this equation is derived from P1 V1 power gamma is equal to P2 V2 power gamma. Then we eliminated this pressure ratio here. So what did we do? PV is equal to MRT, and in place of pressure I can write MRT by V. So in place of pressure I wrote T1 V1 power T1 by V1 power gamma, T2 by V2 power gamma, and then we got T1 V1 power gamma minus 1 is equal to T2 V2 power gamma minus 1. So then we reduced it to T2. So T2 is equal to T1 here, P1 by V2 whole power gamma minus 1. So that is what we said. This is T1 R power gamma minus 1. So T2 is equal to T1 R power gamma minus 1. Now let us calculate this T2. Let us calculate this T2. So T2 is equal to, therefore, T1 was given to us. T1 was 311. So 311 is equal to the value of R we have found out 6.91. 311. The value of R is 6.91 power. Now this gamma minus 1 is 0.4, 1.4 minus 1. So let us solve this. Now unknown is x alpha x divided by 311. Now alpha equals 6.91 power 0.4. Now let us go for shift. solve for x is equal to 0, and then we have T2 is equal to 673.83. T2 is equal to 673.83 Kelvin. Now we have got the value of T2. All we did this in order to get the value of T2. Okay. Now let us come back here to QS. Now 0.718 and T3 is 6, T3 is given to us. T3 is 222 Kelvin. 222 minus 673.83. So therefore, we'll get the unit in kilojoule per kg Kelvin is a CV unit, and this is in Kelvin. So we'll get the answer of heat supplied in kilojoule per kg. Alright. So 0.718 into 223 minus 673.83. So 1112.3 kilojoule per kg. So once you have the value of heat supplied, I think now we can come back here and say therefore efficiency is 53.84. So I am coming back to this equation. So 0.5384, I am not using 100 here, so I am writing efficiency in terms of 0.5384 divided by is equal to W divided by heat supplied 1112.3. So therefore work transfer will be 0.5384 into 1112.3. So that will be 598.86 kilojoule. Thank you.